So hello everyone, we'll continue our discussion about the data link layer. So in the previous class we talked about framing and also we talked about the CRC. So we said the data link layer has to make sense of the bits. So we want to look at the set of bits that we receive as a message. And we need to know when it starts and when it ends. So we said that you can have a special sequence to tell you when it starts and when it ends. And we have to make sure that this sequence doesn't appear somewhere in between. Otherwise, there's a problem. We might think that the message is beginning somewhere here. Okay. So we said that you do something like bit stuffing. That's one of the solutions used by HDLC protocol. So we also said that we use the CRC in order to detect errors. So if at all there are some bit errors over here, we want to detect it, and if at all there are some errors, we might just discard the frame. Okay, so this entire message is called the frame. Okay, and the frame is the term used at the DLL. Okay. So why this CRC? So one of the things we saw, one of the good points was that it was very easy to generate. You just have some delay elements and you have something like a shift register where the bits are going, let's say with the most significant bit going in first. And you just have to do some XORs and so on within that circuit. It's pretty fast, and once you send this entire message through, all these bits through, you will have the CRC stored over there in that circuit, which you can use. So it was very easy to generate. Also, another point which may not have been very clear in the last class is that this message can be of any size. Let's say messages of different sizes. Okay, so what are we doing? You have this CRC circuit. And you have data bits coming in. If you look back to that lecture or the notes for that lecture, you'll see that I can keep pushing in as much data as I want. And once the last bit has gone in, then the CRC is there present in the circuit. So I can have any number of bits here. So we said n bits. But n is not fixed, it can be variable. Okay, so probably the better term here is not different, but variable sizes. Okay. So what we are doing is you have suppose you have suppose your that n was some number, right? So suppose n is equal to 10. That means the total possible messages that you can have here, okay, is or let's say the data part over here. Let's just call this data. So the total data types that you can have of length n bits is 2 to the power of 10. And suppose the CRC is of 3 bits. So this is just an example. So then we are concatenating the data and CRC. and we have 2 to the power of 13 of these. Okay, so data plus CRC would be embedded in this space, but not all of these are valid. So we said only few of them are valid. So there is a mapping from each of these elements. So all of these data words are possible, but only few of these are valid. So there may be many other points in this space which are not valid. So this helps us detect if errors have occurred. So suppose there's a flip in a bit either in the CRC or in the data, then one of these might get mapped to some other point over here, one of these blue ones, and we will run it through the circuit again, the CRC circuit, and we'll be able to easily find out that that is an invalid sequence of bits which we got, okay, because the CRC is invalid. Okay. So this is very good, and of course in this example n is 10, but in general you can have any value of n and you can always generate a CRC for it. Okay. But the question is, what sort of bit errors can the CRC actually detect? Okay, what is a good way to generate a CRC? Okay, so we started with, let's say in the last class, I think we looked at 1101, which was the divisor, and we divided the input data string when we considered it to be a binary data, binary word, and we divided it, and we used the arithmetic for Galois field 2, where addition and subtraction were just XORing, and the remainder turned out to be the CRC. But you might wonder, why choose this 1101? What if we choose something else? Okay, and I mean, what sort of errors can we detect this way? And that's what I wanted to discuss in today's lecture. Let us begin with some mathematics which will help us analyze CRCs. So remember last time we said that when you add or you subtract in GF2, we essentially are going to use XOR. And what we are going to do here is we are going to represent each of these binary numbers, like this divisor you have over here. We are going to write them as polynomials. So how are we going to do this? And of course, when we do things like multiplication and division and so on, we are going to do multiplication and division using these polynomials. So what would 1101 be equal to in this polynomial representation? It is going to be equal to, we're going to write this as x to the power of 0, that's 1, x to the power of 1, x square, x cube. So we're going to have 1 times x cube plus 1 times x square plus 0 times x plus 1 time x power of 0. So essentially this divisor is going to be represented as x cube plus x square plus 1. And what if I multiply this by 1, 1? So let's look at it before, like what we had before. Suppose I was multiplying this, I'd have 1101, and 1 1 0 1, like we do binary multiplication, but it's just that when we add, we're going to use XOR. So we end up with 1 1 1 1. So we are XORing these two bits. 1 plus 1 is not 2, 1 plus 1 is 0, okay, because we're just XORing them, and then we have 1 over here. And what is this equal to? Well, it's, if you think of this as being x to the power of 0, x power of 1 and so on, x square, x cube, x to the power of 4. What this corresponds to is x to the power of 4 plus x square plus x plus 1. Okay. Right? The x cube term is not there because we have a 0 in that position. So let's see if we can do the same thing. We can do the multiplication but using these polynomials. So suppose what is this? It's just x plus 1. And let me just call this generator. So sometimes it's called generator. I've used the term divisor. So it's used to generate the CRC. So it's called the generator. But we can also think of it as a divisor because we had to divide in order to get the CRC. So what is this x plus 1? So what if we multiply? So let me call this c of x. So suppose I multiply c of x with 1 plus x. What do I get? Well, it's going to be x cube plus x square plus 1 plus I'm going to multiply everything by x, so I'm going to get x to the power of 4 plus x cube plus x. Okay, so this is where I'm multiplying c of x with x. So what is the resultant? It's x to the power of 4 plus x cube plus x cube, I'm just collecting the terms, plus x square plus x plus 1. X cube plus x cube is, we are adding up 1 plus 1, so we get 0. So we end up with x to the power of 4 plus x square plus x plus 1. So this is as expected, we're getting the same thing. So instead of dealing with these binary numbers like this, we can think in terms of polynomials. Of course, we have to do the arithmetic appropriately, where addition is done by XORs. So how is this going to help us in analyzing CRCs? So let's think about it. So what do we have when we are transmitting? So suppose I transmit a particular bit string. So let's say that the code word that I transmit, and what is the code word? It's nothing but the data word and the CRC. So suppose that bit string is represented as p of x. Okay, whatever that is, it may be 1 0 0 1 whatever, right? And at the end, of course, is the CRC, whatever it is, right? I'm just creating this example. So suppose this is the code word that I transmit. Now the code, some of the bits could be in error. So how do I represent the error in this particular mathematical notation? So let's call the error bit string e of x. So what does this E of x look like? So suppose the third bit from this particular end was in error. Okay, so what would E of x look like? It would look like you would have all zeros, but you would have a 1 over here. So suppose the third bit was in error and some particular P of x was sent. Essentially what you receive is the sum of those. So we are going to receive P of x plus E of x. And plus is again going to be implemented using XORs. Okay, so in this particular example there was only one bit in error. So what if the third and the fifth bit were in error? What would E of x look like? Well, again, as you would expect, it's straightforward enough. Third and fifth bits in error. This means that E of x is, we'd have 1 0 0, but we'd also have 1 in the fifth place and then zeros over here. Okay. So I think you have the idea now what we are doing. So we represent these bit strings as a polynomial in terms of x. Okay. So let's look at this. So suppose this is what we receive, okay, and suppose these are the errors. What do we want the CRC, what exactly do we want the system to give us? So we said essentially we are going to divide by this divisor, whatever the divisor we've used, and if the resultant is 0, then we say that there is no error. Okay. So we divide the received polynomial by C of x, and if the resultant is 0, then we say that there is no error. Of course, this could be wrong too. I mean, maybe there were so many bit errors that we actually shifted from one valid code word to another one. Okay, that may be possible, and then of course we'd be making a mistake. Okay, but we want to see at least what sort of errors we can catch. Okay, so essentially we want to ask the question, what E of x's will we be able to catch, meaning that when we divide, the resultant will not be 0. Okay. So what we want is that P of x plus E of x divided by this generator is not 0 if E of x is not 0. This is what we want. But this is only in an ideal world where for all E of x's we would get it. Because really E of x could push this code word to another valid code word, and then obviously we are not going to, we are going to end up with 0, so this won't be true. So let's think about it. So what types of errors can we catch? And definitely what we want to be able to do is we want to be able to catch single bit errors. So let's think about it. So we have single bit errors. So what would E of x look like? So just one bit is in error. So essentially this is a polynomial of the type x to the power of I, okay, for some I. Okay, and I can go from 0 all the way to the last bit, right? So we said there are n plus k bits. So that means I can go from 0 to n plus k minus 1. Okay, I belongs to n plus k minus 1. Okay. So how do we choose C of x? So we have to choose C of x so that when I divide, I shouldn't get 0 over here, okay, for this type of error. So let's think about it. So what should C of x be? So P of x plus E of x divided by C of x, I can write it as P of x divided by C of x plus E of x divided by C of x. Now the way we've constructed the CRC, this is actually going to go to 0. The code word is indeed divided by C of x. Okay. And the question is whether x to the power of I can be divided by C of x. Okay. So what we are going to do is, let's say that if C of x is of this form, x to the power of, I beg your pardon, so CRC is k bit, so C of x itself starts from x to the power of k. Okay, and suppose I go all the way up to 1, so that means that the first bit in this C of x is 1 and the last one is also 1. Okay. And I have anything here, so zeros or ones, then we can show that this type of E of x is not divisible by C of x. Think about it. Is it possible for C of x to divide E of x when E of x looks like this? So essentially, what does it mean for C of x to divide another polynomial? It means that C of x multiplied by something else, let's call it D of x, is equal to E of x. We should have something like this. If C of x divides E of x. So is this even possible? So D of x is going to look like some polynomial. It's going to be x to the power of, let's say, m plus, right, x to the power of q, let's say, okay, something for some mn q. Okay, and of course q could be 0, it may not be also. So can you multiply something like this with C of x, where we had x to the power of k plus something in between and x? So can we multiply this and get x to the power of I? And you can see this is not possible, I mean, because what is going to be the smallest term that you get over here? We are going to end up with x to the power of q. Okay, when x power of q, all others will have higher order values of x. Okay. And the highest power is going to be x to the power of k plus m. Okay. So when these, so how am I doing this? Well, when these two multiply these two terms, okay, we're going to get x to the power of q, and when these two multiply, we'll have x to the power of m plus k. Okay. And no other terms over here are going to give us either of these extremes. Okay, because whatever you have here is going to be larger than x to the power of q and going to have higher power, and whatever you have here is going to be higher than x power of 0, right, other product term. So this, you will always have at least two terms, two powers of x's in the resultant polynomial, and you will never be able to write it as x to the power of I. Okay, so this is, you are never going to have this equal to x to the power of I. Okay, so we are in business, so essentially it's saying that if you want to be able to detect single bit errors, your divisor should be of this form, x to the power of k plus, and at the end you should have 1. I mean, if you have this, then you're guaranteed to take care of single bit errors. Okay, there may be other choices of the divisor too, which take care of these sorts of errors. Okay, but definitely if c of x has this form, it will be able to detect all single bit errors. Okay, so that's what we've ended up proving. And our earlier example was 1101, so it was x cube plus x square plus 1. Okay, so it did have that particular form, so it will be able to detect single bit errors. So can we do better than single bit errors? Because what if there are 2 bit errors and so on? So let's discuss that. So 2-bit errors. So E of x is going to look like this. It's going to look like x to the power of j plus x to the power of I, and let's assume j is greater than I. So we can write this as x to the power of I times x to the power of j minus I plus 1. Okay. Okay, and what I am going to do is I am going to write these polynomials in terms of these sorts of products where each of these terms cannot be reduced further to fewer number of terms. So I cannot write this as a single term, I have to use at least 2 terms. Okay. And this one too, I can't reduce the number of terms, I just have a single term, I can't make it 0 terms. Okay. So we're going to write each polynomial as a product of irreducible polynomials. So effectively what I want to do is I am trying to write e of x in terms of some irreducible polynomials. Of course, in this example it's going to look like this, but in a general case it looks like this. You have several of these divided by, and let's say c of x can be written as another set of irreducible polynomials. So what do we want over here? Well, suppose in what case is c of x going to divide e of x? Well, when we are going to be able to cancel all of these terms at the bottom with terms at the top. Okay, that's when we are going to have c of x being able to divide e of x. Okay. So now let's think. Suppose c of x has the form just like we had in the earlier case, x to the power of k plus something like this plus 1. Okay. Now we cannot factor out something like x to the power of I from here, or any factor of x out of here. Then no f, let's say L of x, right, is of the form x to the power of let's say beta, for some beta. Okay. So you can see that, I mean, because if at all, what does it mean? Suppose you can take x to the power of beta out of this, then the smallest term would have to be x to the power of beta, should have x to the power of beta, right? So we cannot, essentially what I'm saying is you cannot write it up in this form. And some other polynomials over here. Okay, so this is a good point, because that means that we are not going to be able to cancel any of these terms. When we take the ratio, when we take x to the power of I, x to the power of j minus 1 plus 1, and we are going to divide by c of x, which is f1 fx fm of x, okay? These terms, x to the power of I terms, are not going to cancel with any of the terms here. So the question is whether all of this entire product, this c of x, is going to divide x to the power of j minus 1 plus 1 out. Okay. Okay, so it's a little bit of a tricky question, because you might think, how is that going to happen? Because c of x has this form, x to the power of k plus something something plus 1. You know, how here there are just two terms, and there may be only an exceptional case where you're going to be able to divide it out, right? Where j minus 1 is j minus I is equal to k or something like that. Okay? But we have to be very careful over here, because we are not dealing with binary polynomials. It's possible that something of this form, that you have x to the power of k plus something something plus 1, and you multiply it by some other polynomial, and you might actually get out something which looks like this. Let me not use n. Let's say let's say some gamma, okay, plus, and this you can have for a large gamma. That is possible. You can find examples like this. You can start with x to the power of k and so on plus 1, multiply it, and all the intermediate terms might go to 0 because of the XORing that might happen. Right? So you have to be very careful. You can't just eyeball it and figure out that something divides something else or not. So it is actually possible for large j minus 1 values for something like this to divide it. Okay. So the question is, how are we going to choose c of x appropriately? Okay. So by the way, what does it mean for j minus I to be large? It means, so j and I are the positions where e of x is 1, or the error bit string is 1. Right? So you have zeros in between. So j minus I is just the distance between this. Okay. So it's possible that if the distance between these is quite large, if you haven't chosen the c of x appropriately, this is c of x, c of x might actually be able to divide this, which means that we won't be able to detect that these bit errors occurred. Okay. So this is where the mathematics of these polynomials come in. Okay. So let's talk about the, let's give a definition which is called the order of a polynomial. So the smallest gamma such that c of x divides x to the power of gamma plus 1 is called its order. Or sometimes it's called its exponent. Now the good thing is that mathematicians have figured out how to be able to find c of x, okay, which has highest power x to the power of k. So this is your c of x. So they know how to find a c of x so that its order is actually going to be equal to 2 to the power of k. So it is known how to find c of x of the form x to the power of k plus so on plus 1 such that it has order 2 to the power of k minus 1. So this is very nice. So that means suppose k is 3, what we took in our example. That means it will have, you can find such a c of x such that its order is going to be at least 7. Okay. So which means that as long as the bit errors are not 7 apart, it's less than 7 apart, then we'll be able to detect it. Okay. So that's going to limit the length of the particular code words that we sent out, right? Because if you have a very long code word, I mean, in the worst case, you'll have the first bit in error and the last bit in error. So j minus I is very, very large. Okay. So if we are allowing a j minus I at most 7 in the case that k is equal to 6. K is equal to 3. Okay, so you would want to have a code word small so that you can detect all 2-bit errors. Okay. What if k is larger? You know, in practice, of course, we don't deal with k equal to 3. We might have 16, something like that. Because in that particular case, we can have longer code words, because even if the bit errors, the 2-bit errors, have bits in error which are far apart, but it's less than 2 to the power of 16 apart, then we are in business. We'll be able to detect it. So suppose k was 16, and in practice you might use something like 16 or 32. Okay, so this means c of x is of this form. Then it will not. Then we can find a c of x such that it will not divide x to the power of p plus 1 for p less than 2 to the power of 16 minus 1. Okay. So in practice, what would this look like? We would have data and CRC. So the CRC is here and the data bits are here, and this would be 16 bits. Okay. And as long as this length, this total length, is less than 2 to the power of 16 minus 1. Okay, so that's a fairly large number of bits. Okay, so you can have a very long code word like this, or a very long message, less than 2 to the power of 16 bits. And in that case, if you get 2 bits in error, you will be able to catch it with this particular CRC. Okay. Okay, so it is possible to come up with such CRCs which will be able to detect all 2-bit errors, provided that the 2-bit errors are not too far apart. And as long as your overall code word is smaller than that maximum distance, then you're going to be able to detect any 2-bit errors which might occur. Okay, so we are in business. We know how to detect single-bit errors, and our friends the mathematicians can pull out some generators or some divisor polynomial c of x which will detect 2-bit errors, which is good enough for our practical purposes. So can we do something more than that? So can we detect all odd numbers of errors? So what does this mean? This means e of x is of the type x power of j plus x power of I whatever, and there's an odd number of terms here. So can we catch all of these? Because that would be very useful. I mean, you can, how many types of errors can you have? Either an odd number of bit errors or an even number of bit errors. And if you get all the odd errors, then that's pretty good. I mean, maybe we figured out how to get single bit errors and 2-bit errors. But if we can get let's say 3-bit errors, 5-bit errors, 7-bit errors and so on, then that's really good. Okay. So how is it possible? Can we come up with a way to create an appropriate C of x so that we'll be able to detect all errors of this form? Now what I'm going to claim is that that if C of x has 1 plus x as a factor, then it will not be able to divide E of x of this form. So if C of x is of the type 1 plus x times some other polynomial, then C of x cannot divide E of x of this form. Okay. Which has an odd number of terms. Okay, so basically what we are saying is that E of x cannot be written as 1 plus x times any g of x. Okay, so you will never be able to find a g of x of this form. Okay, and this is necessary because this is an irreducible polynomial. So you should be able to write E of x in terms of 1 plus x, otherwise it will not cancel with this 1 plus x of C of x. So how are we going to show this? Okay, so basically we are saying you give me any polynomial g of x and I multiply it by 1 plus x, and I'm not going to be able to have an odd number of terms at the end. It's going to be an even number of terms. Okay. So let's take an example. So suppose we have as an example, so suppose I take 1 1 0 1 1 1 0, this is my example, and let's say I have 0 1 0 0 1 1 0 0 1. Okay. So this is my G bit string. Okay, and of course for g of x I would write it as a polynomial. Okay, but I'm just writing it in bit forms like this. And now I multiply it. So this is when I multiply by 1. When I multiply by x, essentially I'm just pushing these 1 bit to the left. Okay, that's what it means to multiply by. So I'm having 1 over here. Here I end up with 1 1 0. So here I have 1 0, here I'm going to have 1 1 1 0. Okay, and suppose I want to add this. So remember, there are no carries over here, so we don't have to worry about that. So let's focus on one of these particular cases where I have a particular string of ones. So let's focus on these two over here. So I have a string of ones, let's say preceded by 0. What is going to happen when I add 1 plus 0? I have 1. Here I end up with 0 in between, and this last 0 which precedes this set of ones ends up as a 1. Okay. Okay. So let's look at this particular case over here. I'm looking at these bits. So I have 1 here, and this also becomes a 1. Okay. What about this case over here where I had 3 ones? Okay, so I'm just going to put a 0 here. So I'm focusing on these, a burst of ones preceded by a 0. That's how I'm going to look at it. Here I have 1. Okay. In between everything becomes 0 because I have a burst of ones, and at the end I have 1. Okay. So each of these, of course here too I'm going to have 1, 1. Always has this particular form. If I have a burst of ones, I'm going to end up with zeros in between, and it's going to be surrounded by ones on both sides. Okay, so for every such, I can split up any g of x, any such number, any such binary string, into places where I have consecutive ones. Okay, and of course it has to be preceded by 0. Otherwise that would, if this was also 1, it would be part of the burst of ones. So I take all of them in the preceding 0, okay, and I look at those bits, and I can show that you're going to have only 2 bits coming out. So there are 2 ones, okay, in all of this. Okay. So whatever I end up with will have an even number of ones. Okay, which means that you will never end up with an odd number of terms. Okay, so the number of terms over here is going to be even always. Okay, so you're never going to be able to write 1 plus x times any g of x as an odd number of terms. So now again we are in business. If you can find a c of x which has factor 1 plus x, then it's going to be able to pick out all odd number of errors. Okay. Now it's also, so this is of course one claim that we've been able to prove. There is another claim which I am not going to prove, but it can be shown that if c of x has an even number of terms, then it will not divide e of x which has an odd number of terms. If e of x has an odd number of terms. Okay, so this is quite a powerful statement. So I don't have to try to factor out c of x and try to see 1 plus x is a factor. If c of x has an even number of terms, then we are done. That means we are saying that we'll be able to catch all odd number of errors. Okay, so I'm not going to prove this particular statement. Okay, probably we will have to use some sort of induction or something like that. Okay, so you start with an even number of terms, and then you have to do something like this. You have to show that you take any product of that, you will end up with again with an even number of terms. Okay, you will not have an odd number of terms. Okay, so this mathematics is helping us. It shows us when we are going to get rid of, we're going to be able to detect single bit errors, when we are going to be able to detect 2-bit errors and odd number of errors. Okay, so what is used in practice? Let's look at that. And HDLC, for example, uses a particular CRC. And it uses CRC 16. Okay, so it uses CRC 16 IBM. So these have got names. It was probably invented at IBM. and c of x is of this form: x to the power of 16 plus x to the power of 15 plus x square plus 1. So this is an even number of terms. We are in business. Okay. And of course we are going to be able to detect 1-bit errors, right? Okay. And CRC 32 is used by some protocols. So CRC 32 is of this form. There are lots of terms. (23), 22 is also there, plus 16. So there's a gap over here, 6 bits. Okay, and here too there's a gap of 6 bits. And smaller gaps in between. So I'll just write this out. Plus x power of 8 plus x power of 7, 5, 4, 2, 1, 0. So these are standard CRCs. If ever you have to implement a CRC, rather than working out the math, it probably makes sense to just use one of these standard CRCs. Okay, so if you want to implement this in hardware, you can just have a shift register circuit, okay, and with appropriate XORs like we discussed. Okay, so this one will be much easier than this one to implement. There are fewer XORs to be done here. And once you send your full data word through, you're going to have the CRC ready, right, in that shift register itself. Okay. Okay, so this is all that we wanted to talk about CRCs at the link layer. Okay, and so link layer is going to do some amount of error detection. And of course, coding theory is a very advanced subject. You have full courses on it, right? And normally, certain communication systems, it may not be enough just to detect the error. You may also want to correct the error. Okay? So you have to have codes which will say that suppose the number of errors is less than a certain amount, then I can always correct perfectly without, I can correct for those errors always. Okay, but of course if there are too many errors, you can't do anything, because then you may go from one valid code word to another valid code word. Okay, so that nobody can fix. But you may be able to design codes in such a way that the Hamming distance of the code is quite large. Okay. So this is all that I wanted to talk about. So for example, if you're doing satellite communication or something, it makes sense to actually correct for the errors and not just detect them, just because retransmitting all the data might be expensive. The delays are large and maybe the bit rate is also quite low.